Okay, so ladies and gentlemen, welcome to the Young Researcher Best Paper presentation of this Amases remote meeting. I leave immediately the floor to Francesco Cordoni, who is gonna present the instabilities in multi-asset and multi-agent market impact games. Francesco, you have around 25 minutes for your presentation, and then we left the floor to questions from the audience. I will warn you when you have 5 minutes left. Okay, thank you.
Okay, thank you. And thank you for giving me this opportunity to present my joint work with Fabrizio Lillo in instabilities, multi-asset and multi-agent market impact games. So in this presentation, I'm going to use multi-market impact games to study and to investigate some possible sources of instabilities. But why market impact games? Because we know from the recent history of financial markets that markets tend to exhibit some kind of instabilities for very short time scale, like in the flash crash. And the report on the flash crash suggests that the hot potato volume effect generated by high-frequency trader at least contribute to the acceleration of the fundamentally seller algorithm which generates the flash crash. And this kind of observation were observed by Shin and Zhang in equilibrium strategies between two agents in a market impact model, which is actually the framework of market impact games. So this explains why market impact games are the theoretical and mathematical tools for investigating and studying market stability. We know that the flash crash was not only about a mini crash, and since the market impact framework of Shin and Zhang is related to a market with two agents and one asset, naturally question arise about if we can extend the framework to study market stability. So for instance, how market is affected by the number of traded assets, or so what about if we increase the complexity of the market in terms of liquidity factors, or if we increase the competition in the market, and also the presence of heterogeneous agents affect the stability. So we try to answer to this question by, first of all, formalizing the concept of market stability in market impact games, and we extend the framework of Shin and Zhang to the multi-asset case, where we solve analytically the Nash equilibrium, and also we characterize the market stability. And then also we discuss also some possible we discuss also the market stability in the multi-agent and heterogeneous agent case. So I start by presenting the standard framework of market impact games and market stability, and then I show some the result for the multi-asset and multi-agent and heterogeneous agent case. So essentially, in a market impact games, we have two traders who wants to trade the same asset during the same time interval. And since market impact, an optimal execution schedule should take into account also the presence of the other trading strategy. So typically the approach is to define and study and find the Nash equilibrium. So we start with the definition of an affected price process, which is a right continuous martingale defined at a given probability space. Then a trader wants to liquidate the asset during the trading time grid, okay, following an Amazon strategy, where it essentially is a sequence of random variables which are bounded and adapted to the filtration, and also must satisfy the inventory condition, which is the second equation. So the interpretation is that a short position in the asset corresponds to a positive inventory and negative for the long position. Then we use the transient impact model to describe how the trading activities of the two traders impact and affect the price dynamics. And so we introduce for each trading time decay, we introduce the decay kernel, which multiply the cumulative order of the traders. And the decay kernel is describe the price impact of a unit buy or sell over the time, and must satisfy the usual condition for no dynamic arbitrage, so to avoid price manipulation, so it must be convex, non-increasing, non-constant, and so on. So then a trader, the aim of a trader is to minimize the liquidation cost. So we have to define what is a cost for a strategy given the other trader strategy, which is defined as the book value position of the initial position at time 0, because we consider implementation shortfall orders, plus the sum here in the right, which is essentially the liquidation cost, which can be divided for each time step in 3 components. The first component is related to the price movement caused by the order at time k. Then we have a cost of latency, which is the red one component, where the time priority is described by a Bernoulli game. And also we have a temporary impact, which is the blue terms, which is a transaction, is a model for the transaction cost, and a proxy, so for the slippage cost, where theta is the transaction cost level, which is, as we will see, is very important for market stability. Then we define the Nash equilibrium in terms of expected cost of a strategy. And the result, the main result of Shide-Zhang shows that there exists a unique Nash equilibrium, and also it is deterministic, and they provide a closed formula solution. So if we consider the following setting, where we have 2 fundamentally seller wants to sell the asset, we can obtain the optimal strategy for the 2 traders, where this plot here exhibits the optimal volume to trade in the asset for the fundamentalist. Then we can compute the cumulative impact or the cumulative drift due to the trading activity of both traders, which is the red line, and the associated price process. Then we observe that when theta is close to 0, the Nash equilibrium starts to exhibit some huge oscillations. And these oscillations are also propagated in the price dynamics. And moreover, we can define, so if we define a spurious oscillation as a sequence of trading times where the orders are consecutively composed by buy and sell, it's possible to show, and this is actually what shows Shide-Zhang, that there exists a critical value for the transaction cost level, such that for all thetas which are greater than this critical value, the equilibrium strategies do not exhibit spurious oscillation. And also we can characterize the critical value in function of the decay kernel. Why we have to avoid this kind of oscillation? Because as we have seen in the previous slide, this oscillation affect the price dynamic, and so also the consistency of spot volatility estimation. And moreover, a behavior like a spurious oscillation corresponds to a transaction triggered price manipulation in the optimal execution literature. So we introduce 2 definitions of market stability. We say that the market is strongly stable if for all transaction cost level, the Nash equilibrium does not exhibit spurious oscillation for all inventories. And we say that the week is stable when there exists an interval of transaction cost levels such that for all theta in this interval, the Nash equilibrium does not exhibit spurious oscillation. And we have another interpretation of the Shide-Zhang result. So we extend the framework to the multi-asset case by, first of all, we observe that the definition of an affected price process and amnesty strategies are straightforward from the one asset case, with only to pay attention that now a strategy is a matrix, okay? Then we introduce in the affected price dynamics the cross-impact effect, where the cross-impact effect is an effect related to mispricing in assets which are correlated, and this is introduced mathematically by considering a multivariate function which describes how the impact of an order to one asset also affect the price of other assets, okay? And we know that in order to avoid price manipulations and so dynamic arbitrage, the cross-impact function must be linear and symmetric. Also, we assume the same temporal dependence of the kernel among the assets as empirically observed by Master Matteo and others, so that we can split our cross-impact function into components, the decay kernel, which is univariate function, times the cross-impact, the so-called cross-impact matrix. And so we have our definition of affected price process in the multivariate case. Then, just to give an intuition of how to obtain the Nash equilibrium, we use the spectral decomposition of the cross-impact matrix. So we can obtain for each orthogonalized virtual asset the related Nash equilibrium. And then we can recover the solution for the initial inventory by using the inverse transformation. So, and we find an interesting result by considering the following setting, where we have a market with two assets and two agents, a fundamentalist seller and an arbitrageur, where the fundamentalist seller wants to liquidate only the first asset, and the cross impact is described by this matrix here. Then we find that for the fundamentalist is optimal also to open a position in the second asset. And due to the cross impact effect, and because he or she wants to protect him or herself against the predator trading of the arbitrageur. But what about stability? So we observe that the possibility to trade one or more assets does not improve the strong stability results. So we focus on the weak stability, and we are interested to study if the instability is still present also when we increase the number of traded assets. So we introduce the definition of asymptotically weakly stable, which is essentially a market which is weakly stable also when m goes to infinity. And then we show how to relate the liquidity factor, so the spectrum of the cross-impact matrix, to instability. And in particular, the critical value is obtained by the one asset critical value times the maximum eigenvalue of the cross-impact matrix. So we studied some realistic case of cross-impact structure. So we start with the simple one-factor case when we have only one parameter which describes the cross-impact, where Q is a metric which is when there is one in the diagonal, and then all the off-diagonal elements are constant equal to a parameter which describes the cross-impact. And since the maximum eigenvalue is proportional to the dimension of the market, of the number of traded assets, the market is not asymptotically weakly stable. And we have an analogous result if we consider a generalization of the one-factor case, which is the rank one modification matrix, where beta is can be interpreted as, for instance, a correlation of the stock, of the E-stock with the market. But this is not interesting because the empirical evidence say that the cross-impact matrix or propagator matrix is a block matrix where each block is related to economic set. This is a study of an empirical study of Master Matteo and others that I have cited also in the previous slide, where they exhibit where they fit the propagator matrix. So we study the block matrix case where each block is across one-factor matrix, and we show that if the average number of stock in a cluster diverge when m goes to infinity, then the market is not asymptotically weakly stable. Moreover, we show that the one-factor case is the most stable cross-impact structure. More precisely, since comparing different metrics is not straightforward, we first of all introduce the set of cross-impact metrics where the average cross-impact is fixed, or the sum of off-diagonal terms are fixed, is fixed for this metric. So, and in this set of metrics, we show that the one-factor metric is one with the smallest, largest eigenvalue. So this means that if we fix the number of stock, and if we increase the complexity of the cross-impact structure, the market stability is deteriorated. Okay, so so for the multi-agent case, we have a market. We study a market with with J agents and one asset. Okay, and then the affected price process is trivially defined by considering the cumulative impact of all the orders of the agents. While for the expected cost is not so trivial, because for each trading time we have to consider all the possible time priorities, and so permutation of the trader. And then we also introduce a scaling parameter beta for the kernel function, because so that when G, the number of traders, increase to infinity, the impact of the single agent becomes negligible in comparison to the cumulative impact of all the other agents. Then we estimate the critical value in function of the number of agents, and we find that it's an increasing function of J. And we also observe that the relation seems to be relaxed when beta increases, the scaling parameter increases. So, okay, what about the heterogeneous case? So we study the standard framework of market impact games with two agents and one asset. And we assume that both agents are fundamentally seller, but we assume that there are differences in terms of their trading skills. Okay, so we analyze three situations. In the first case, the two traders have different permanent impact, because the permanent impact, traditionally, market microstructure theory, is a measure for informativeness of trades. So an agent with a small permanent impact might be interpreted as a noise trader, but we find that the market stability is not compromised by the presence of different agents with different permanent impact. So in this presentation, I focus only on the two last points, where we have different temporary impact, so different transaction cost level, and also the two traders have different trading speed. We name the traders who has a privilege, both in terms of theta or trading speed, as the high frequency trader. So for the first case, we have no problem with stability if the high frequency trader and also the other fundamentalists have a transaction cost level which is greater than the critical value. But in a market when only the high frequency trader has a transaction cost level which is smaller than the critical value, then the instability comes up also for the other agents, even if he or she has a transaction cost level which is greater than the critical value. So finally, we know, we consider the other case of heterogeneous agents, and we know that in the standard setting that we have to decide the time priority, and which is moderated by a Bernoulli fair game. Then we now for each trading time K, the Bernoulli game is no longer fair, and the probability P is the probability that the second trader places an order before the first trader. So we compute the critical value in function of P, and we find that the presence of fast traders makes market more prone to instability. But we observe, by looking the size of critical value, that this effect is relatively small compared to the other factor or other sources of instability that we have seen in the previous slide. So, okay, so in
You have
conclusion,
5 minutes. Oh, okay.
conclusion,
Thank you, Francesco.
in conclusion, in this work, we use market impact games to study some possible sources of instability. And we find that an increasing in the number of traded assets, in the complexity of the market in terms of cross-impact structure, in the competition in the market, and also in the heterogeneity, makes market more unstable. And so, if we are a policy regulator, so we want to prevent instability, according to this simple framework, we need to monitor the number of traded assets together with the cross-impact level, and then choose an appropriate transaction cost level, where this plot here is the plot of the critical value surface in function of the number of traded assets and cross-impact level in a market when the cross-impact matrix is described by a one-factor matrix. So thank you, and thank you for your attention.
Okay, any question from the audience? Any question? If you have any question, you should type your question in the Q&A box. No? If not, then I have a question for Francesco, because your analysis relates to the theory or to the literature in asset pricing, where you study the equilibrium in relation to bubbles also. And usually in that sort of environment, you have a standard definition of agents in the market, and they are divided among hedgers, speculators, and arbitrageurs. And in particular, I was wondering how much your results rely on the presence on a fundamentalist seller only, because when you add commodities to the market, it would be meaningful also to consider fundamentalist buyers, as usually you have the presence of people who want to buy some sort of commodity. And so it would be nice to see or to have an idea on how your results would modify in that case.
Okay, so yes, thank
you
for the question. So actually in the work we study some trading profile, and we consider 3 types of traders. We consider the fundamentalists, the arbitrageur, and also market neutral, where market neutral is a sort of arbitrageur when the cumulative order, so the cumulative inventories, is 0. And we analyze, for time reason, I have not enough time to discuss in the presentation. So, but we analyze also the trading profile, and also we find that in a market when we have a sort of when we have small traders, okay, and we analyze a situation where we have a fundamentalist seller. All the agents are fundamentalist seller, but there is one which is a big fundamentalist seller, okay, which is, so it means that the volume of traded by the first trader is relatively big than the other traders. And we find that the presence of small trader does not affect the optimal volume strategy of the big one. While in the other situation, we have analogous opposite result. Okay, so it is, but for the stability, I think that is the question related to stability. We have no difference if we consider a fundamentalist or a market neutral, because the stability that we have discussed is characterized by the transaction cost and the critical value of transaction cost and spurious oscillation, and these are invariant from the inventories of the traders. Okay, I don't. Okay.
Yeah, I think that my question was slightly different, because I was concerned on the fact that depending on the different utility functions or the different objectives traders may have, you get different results. For instance, there is a beautiful paper by Rakeland, I don't know if you know it, on economic theory, with other guys, with Bernard Villeneuve, and where basically it studies the impact on the different equilibrium that you get if you have hedgers, speculators, and also commodity buyers who want to buy the security with respect to the futures. But okay, but in any case, your answer was in any case highlighting a nice feature of your model and of your results. Then I have to leave the floor to Paolo Pellizzari, who has a question from the policy point of view. So I read publish the question for everybody. So from the policy point of view, it may be hard to monitor traders, factors, and so on. So Paolo is asking, would you say that, simply put, increasing with your sophistication or without your sophistication, transaction costs may be in general helpful? Maybe I'm thinking to Tobin tax and the like. Do you have any comment? That's a very difficult question to answer.
Yes, I know that it is difficult to know the exact number of traders, because I mean, and also it's not so easy to estimate the cross impact level of the market. And yes, in general, for a policy regulator, a rule of thumb is to increase transaction costs, but not so much, because otherwise it is not optimal to trade. So yes, this is my
okay, your suggestion for the big guys. Okay. Francesco, thank you.
Okay,
Any other question? Any other question from the audience? Apparently not. If this is the case, okay, Paolo, thanks.
Okay, thank you.
If this is the case, so if there are no other questions, I would like to thank Francesco and for his beautiful presentation and for his work. Thank you. And now, if Maria Flora is here, we can give the floor to her.
Good morning, everyone.
Hi, Maria. Hi. Nice to see you. Okay, so Maria Flora is going to present us a fragility of financial markets, the Italian debt not so flash crash. Maria, you have half an hour, but 5 minutes are devoted to the questions. So you have 25 minutes. And thank you in advance for your presentation.
Thank you, Anna, for the introduction. And yes, so thank you. I'm honored of being here. Thank you for having me here. And yes, so actually the title of this paper used to be Fragility of Financial Markets, the case of Italian public debt, so long title. And now it's super short, it's just V-shapes. And this is a joint work with Roberto Renaud, who works at the same department of mine. So what's a V-shape? So to answer that, let's start with a premise. What's a flash crash? So Francesco talked about flash crashes as well. So a flash crash is defined by the Bank of England as a large and rapid change in the price of an asset that does not coincide with, or in some cases, substantially overshoots changes in economic fundamentals, before typically retracing those moves shortly afterwards. So basically the price drops and then rebounds, and it forms a V. It traces a V shape. And these events are pretty frequent in high-frequency financial markets. The most famous one is the flash crash of May 6, 2010 in the US stock market, but there are many other events such as this. There's a list of the most famous one over the past few years. And there's a debate going on around flash crashes. That is, are these flash crashes a problem for financial stability? And in this work, we contribute to this issue in different directions. So first, we argue that to detect market inefficiency of flash crash type, what we need to do is to look at the drift. And specifically, we need to look for sudden changes in the sign of the price drift. And we call these V-shapes. So our definition of V-shape is a sudden change in the sign of the drift. And then we use this insight, this new idea, to develop a novel econometric test, which we call the V-statistic, and which can detect such V-shapes. And so it can detect market inefficiency. And then we apply our V-statistic to a case study. And the case study that we choose is the collapse of the Italian sovereign bond market at the end of May 2018, which was triggered by political turmoil. And we estimate, so we detect inefficiency during the crash, and we estimate that this inefficiency caused almost €500 million loss for Italian taxpayers in just one day. And so we can conclude that these shapes can have serious implications on financial stability and on wealth redistribution. And our work recently attracted the attention of media and regulators. For example, our work was mentioned in Il Sole 24 Ore, Econopoly blog, and it will soon be featured in a Bank Underground blog post, which will appear soon. And importantly, our V statistic was also used in the latest financial stability report of the Bank of England to assess the presence of market distress during the COVID days. And let's see right away how the V statistic works. So this is the same graph that Francesco showed. This is the one you see here is the price of the S&P 500 E-mini futures during the day of the flash crash, the eponymous flash crash, so the most famous flash crash, the one of May 6, 2010. And this is a day when everybody agrees that the market was inefficient. And so we apply our V statistic to this transaction data, and this is what we get. So the red pentagrams here are the values that our V statistic takes. And you see that at the moment of the crash, so right before 3 p.m., our V statistic gets large and negative and highly statistically significant, because the dashed red line you see here is the 1% confidence band. And so our V statistic does its job, and it signals that the market was strongly inefficient on that occasion. But what's the intuition behind our econometric test? So let's formalize our intuition with these three idealized markets. So the first column of this picture represents a perfectly efficient market. Well, it represents the expected price, the volatility, and the drift in a perfectly efficient market. So a market with no frictions. And the expected price, imagine the expected price is at 100, and then imagine a piece of news hits the market. And because there are no frictions, the price immediately embeds the news, the information of the news, and drops to a new fundamental level, 95. And typically this price variation causes higher uncertainty. And so volatility spikes as the news hits and then slowly declines. And what about volatility and what about the drift? Sorry, well, the drift is the first derivative of the expected price, and so it's essentially zero. It's not affected by the news. So this is a perfectly efficient market. But what if there are frictions? Like in reality, in real markets, there are frictions. And so let's have a look at a quasi-efficient market. If there are frictions, the price does not embed immediately the news, but instead the news gets embedded slowly, frictionally in the price, and the price smoothly declines to a new fundamental level. And accordingly, volatility smoothly goes up and then goes down. And now the drift is negative. But what if the market is inefficient? So if there is inefficiency in the market, what we see is the V-shape pattern that we observed before in the previous slide. So the price drops, rebounds, and it forms this V. And what happens to volatility? Well, volatility again spikes. The price variation is higher than before, so volatility is higher, but still the shape that volatility has is essentially similar. So you see that just by looking at volatility, we cannot really disentangle the efficient from the inefficient case. We cannot tell whether we are in an inefficient state. What really changes now is the drift, because there's a cusp here in prices, and so the drift gets abnormally large. First, large and negative, and then large and positive. So you see that the drift suddenly changes sign. And this sudden change of sign in the drift is what we want to look for in data. And this is what our V statistic is going to detect in data, to detect market inefficiency. So this is an idealized market. Let's have a look at another real market. This is the case study that I mentioned before that we were going to use in this work. So this is the Italian government bond market in 2018. And these, you see here, this one is a representative set of government bonds, Italian government bonds in 2018. And the dashed red line here is the day of the crash. So we observe a V shape in each one of these 5 prices on May 29. You see that the shape is similar to the one that we described before. But what happened exactly on May 29? Well, you might remember that in those days there was a heightened political instability in Italy because there was a change of government and there was this new cabinet formation, and so a lot of political uncertainty, which culminated on that day. And the realized volatility captures this heightened uncertainty in prices. And in fact, if we have a look at the realized volatility of those bonds, we can see there is spikes exactly on that day. And the shape that volatility has is similar to the one we described before. But again, just by looking at it, we cannot tell whether the market is in an efficient or inefficient state. And such V-shapes and such occurrences are predicted by economic theory. For example, Grossman and Miller predict V-shapes when there is demand for immediacy. So there is a trader who wants to sell a large order, and he goes to a market maker and he wants the order executed immediately. So it demands for immediacy, and this can cause V-shapes. And this simple economic mechanism can be enriched with a series of frictions. So, for example, Brunner, Maia, and Pedersen explain V-shapes with predatory trading. And all these works associate V-shapes with illiquid markets. And indeed, if we look at a liquidity measure of the Italian government bond market in those days, we can see that this is the bid and ask spread, and we can see that it spikes on the day of the crash. And the shape that the bid and ask spread shows is essentially similar to that of realized volatility. So again, we cannot tell whether we are in an efficient or inefficient state. So let's go back to our intuition. We said that to really detect inefficiency, what we want to look at is the drift. The problem with the drift, though, is that it is well known that it cannot be consistently estimated in a short time window. And so we need a way around this. So let's define our model. This is our log price process X. It's a continuous time semi-martingale. And basically it's a classical Ito semi-martingale, but enriched with explosions. So here we allow for explosions in the drift, both at the left and at the right. And we also allow for explosion in volatility. And now we define our V statistic as the product of 2 different test statistics, T plus and T minus, and this is just a scaling factor. So let's start with T minus. T minus is defined as the ratio of the non-parametric localized estimator of the drift to the non-parametric localized estimator of volatility. And so intuitively, this T minus measures the relative strength of the drift component to the volatility component. And so the trick here is that, and T plus, the difference between T plus and T minus, it's only in the kernel function. So basically T plus is the same. The only thing that changes is that here, the kernel function is a forward-looking one. Instead, in T minus, the kernel function is a backward-looking one. So the trick here, I was saying, is that even though we cannot consistently estimate the sign of the drift in a small time window, we can derive the asymptotic distribution of this statistic. Oh yeah, and this bandwidth H, this H parameter here is the bandwidth that intuitively measures the duration of the crash, so the duration of the V shape. And the kernel function, as I said, is a function that we need to localize the estimators. Okay, so now we can prove that if the drift explosion is sufficiently strong enough, and if the estimation window is large enough, and if the drift explodes both at the left and at the right, then our V statistic goes to infinity. And instead, if one of these three conditions is not met, then the V statistic goes to 0. And we can also prove that this theorem still holds even in presence of market microstructure noise. So now we can finally apply our V statistic to our case study. So these you see here are the values that the V statistic takes for each one of the 5 bonds that I showed in the previous slides. And these dashed and solid, the gray lines, represent the 5% and 1% confidence bands only for the first bond, because each bond has a different confidence band. And so here in this picture, we only included the one for the first bond. And the important thing is that you see that on the day of the crash, May 29, all bonds exhibit strong, large negative values of the V statistic. And the values that the V statistics have on that day have a p-value that is around 1%. So they are statistically significant, and so they provide a signal of inefficiency in the market. And here you may wonder, okay, but why should we care that the market was inefficient on that day? Well, in this case, for example, we should care because there was, during that day, there was a large treasury auction taking place. And the auction took place exactly at the bottom of the crash. So these you see here are the prices of the 3 bonds that were auctioned on that day. And this is the auction time. And you see that the auction coincided with the bottom of the crash. So with the crash, the bottom of the B shape. And so this coincidence implies a strong redistribution effect, a wealth redistribution effect. So it implies a loss for Italian taxpayers, this inefficiency in the market. And we want to quantify the loss that there was on that day. And to do so, we use a parametric methodology this time, and we estimate a Markov regime switching process. So we assume that prices follow geometric motions, and we assume that we can have 3 regimes. Regime 1 is the business as usual regime, so we assume that the drift is 0, and there's a certain volatility level, sigma 1. And then we assume there can be a second regime where the drift is different from 0. This should be the crash regime, right? And volatility has another level, sigma 2. And then we also assume that after a crash, there can be some lingering effects on the uncertainty in prices. And so we assume there can be a third regime where the drift is again 0 and volatility is another level, sigma 3. And then we estimate the parameters of the Markov regime switching model. And this is what we get. So this is the result for one of the 3 bonds that were auctioned. This is the first one, the BTP 1st February 2028. And this, the black line you see is the price of the bond, and this is the day of the crash. And these are the state probabilities of being one state or another. And you see that at the beginning of 2018, it's very likely that we are in a business as usual state. And then as the crash approaches, it's very likely that we are in the second state, the inefficient state. And in turn, a further regime appears now. And finally, eventually, things go back to normal. So we go back, the probability of being in the first regime, the business as usual one, gets very high. And if we have a look at the parameters of that we estimated, we see that, okay, these are the parameters for each one of the 3 bonds that were auctioned on that day. And you see that in regime 1, the business as usual one, well, the drift is 0, and then we have a certain level for volatility. And then in regime 2, the drift gets large and negative, and volatility spikes and gets to a very high level. And then in regime 3, we have there again, drift is 0, and volatility has a third level that is lower than the one of the crash, but still higher than the one of the business as usual state. And so this confirms our intuition that there can be a third regime and that the drift is very negative during the second regime. So now we want to use these parameters to estimate the loss for Italian taxpayers. So we assume that if the market was efficient, so if the inefficiency, the V shape, didn't happen, we would switch from state 1 to state 3 directly without going through regime 2. And so what we do is we simulate Brownian bridges from state 1 to state 3 to connect the prices and to obtain a synthetic price that there should have been if the market was efficient. And then we use this synthetic price that we compute for each simulation to compute the difference with the actual price that we observed in the auction. And if we have a look at the distribution of this difference between the synthetic price and the true inefficient price that we had, this is what we get. So you see that on average, Italian taxpayers lost in just one day, on that day, roughly €500 million, 450 million euros. And the important thing is that this difference is statistically significant, significantly different from 0. So we can conclude that V-shapes are a threat to financial stability, and that what we need to look at to detect the inefficiency that they imply is the local drift. And these are the future questions on our agenda. So basically, we also want to understand what caused this abnormal price movement and what can we change in the market making infrastructure to avoid this, and if we can avoid this happening again at all. So thank you for your attention.
Thank you, Maria, for being so effective and for delivering the presentation so precisely and so on time. So are there any questions from the audience for you? Apparently not yet. Then, Maria, yes, there is one question, so let me have a look. So Claudio Fontana is asking, in the ITO process setting you presented at the beginning of your talk, does the drift explosion have arbitrage implications?
Okay, thank you, Claudio. Yeah, this is a very good question. So there are certain values of the alpha and beta parameters for which absence of arbitrage is not preserved. And specifically, when alpha minus beta is greater than 3/4, so when the drift, the rate of explosion in the drift is stronger than the rate of explosion in the volatility, then absence of arbitrage is not preserved. But this in practice is not a problem for us, because when the drift explodes with a rate that is stronger than the volatility one, then we observe a V shape, and during V shapes, the liquidity conditions are such that it is practically impossible to exploit this arbitrage opportunity.
Okay. Then there is a question by Tiziano Vargiolo. Given that you can detect a flash crash as soon as it manifests, can we effectively hedge it?
Sorry, can we effectively?
Hedge it. So Tiziano is asking if you can hedge against the flash crash. Actually, I have a curiosity here, and the question that relates to Tiziano's one, which is the following. How long does it take to detect the V-shape? In other words, because in your estimator, you have to take backward and forward Yes. So how long does it take in the future to detect where we are along the V letter of the
So
rebound?
yeah. I mean, yeah. Unfortunately, this is not exactly a real-time measure, but still. So, for example, we also study. I didn't present it in this presentation for time constraint, but we also studied the U.S. stock market during the COVID days. So the SPY index, and in that occasions we saw that when there is a V shape, even if we use a bandwidth of 5 minutes, so we only need 5 minutes after the bottom of the crash, still the V-shape can last much longer. So basically after 5 minutes, we know the crash happened, but then the crash can last even for a couple of hours.
And you can realize that you're still on the rebound.
Yeah.
Is there any way to adopt your technology also to predict less, let's say, spiky rebounds? You know that as you have been quoted by so many policy people, you know that now in COVID there is all this speculation about the shape of our rebound that we are expecting. So someone is talking about a U shape, someone about a V shape. Could you eventually think about, let's say, estimating also less drastic rebound shapes or crashes of the time by perhaps modifying?
So, well, this test is designed to detect V shapes.
Exactly.
Because we exploit this sudden change in the sign of the price drift. So, yes. For example, U shapes are not included basically in our alternative hypothesis. So,
and would it be possible to consider? I know that it's not so easy to detect, but because basically you are estimating differences of different orders, perhaps including difference or finite differences in the different parameters.
Maybe
that you use.
We should think about it, but the point, probably the point, is that we should ask ourselves whether U shapes are inefficient as well as V shapes, because here we're looking for inefficiency and probably the most
inefficient one. Is the V. No, I was just asking about the possibility of adapting and extending your statistics to detect other patterns in the market. Okay, other questions? So apparently there are no further questions. Okay, I don't think so. So in this case, I thank Maria very much for your presentation and for your answers. Thank you again. And I would like to invite the next presenter, who is Salvatore Scognamiglio, to join us.
Hi, can you hear me?
Yes, we can hear you well. We can't see you. It says that it's a little bit dark, but it doesn't matter because we can hear you perfectly. So this is the important thing. Okay. And
I will share my slide.
Yes. Yes, we can see everything properly. Okay, so Salvatore Scognamiglio is going to present us a paper entitled Time Series Forecasting of Mortality Rates Using Deep Learning. Thank you, Salvatore. We leave you the floor and you have about 25 minutes for your presentation. Thank you.
Okay, thank you for the kind introduction. This work is a joint work paper with Francesca Perla from my department, Rona Richman from the QED Actuaries and Consultants, and Mario Valentine Wutrick from the Department of Mathematics of the ETH Zurich. In this work, we develop a deep learning-based model to jointly forecast the future mortality dynamics of a large set of human populations. In particular, as you know, mortality is really important for our society because it influences pension plans, healthcare systems, and life insurance industry. Historical data shows that mortality rates have been decreasing over time, especially in the last period, and predicting the future longevity improvement represents an important, at the same time, difficult task. The most popular methodology to forecast the future mortality improvements is the Lee-Carter model proposed in 1992. And however, in its traditional formulation, this model can be applied only to a single population. For this reason, several multi-population extensions of Lee-Carter have been proposed in literature. In our paper, we cite Lee and Lee and the Kleinov model. And however, the intuition behind the multi-population mortality is that similar populations often present some common factor. And for this reason, we expected that multi-population models should produce more robust mortality forecasts. However, these models are usually intended for forecasting the mortality of a similar population. Indeed, they are not so suited to jointly forecast the future mortality dynamics of very different population, for example, Italian and Russian population. And this model indeed are generally applied on a small subset of population, and this subset is decided by the modeler. In this work, we extend the idea of the multi-population mortality modeling, in part considering a large set of human populations. In particular, the aim of this paper, and of course of this presentation, is to explore how large-scale mortality forecasting can be produced using neural networks. When I say large-scale mortality forecasting, I mean the simultaneous production of forecasts for many different and potentially unrelated populations. The neural network model we propose in this paper has some nice property. First, it can be considered as a generalization of a traditional Lee-Carter model. And interestingly, it is able to jointly perform learning and forecasting of many different populations. And another interesting property of our model is that it is able to carry out the feature engineering for us only by processing the raw mortality data. If you want to read our full paper, it is available on SSRN. Instead, the short summary is published in the August issue of the Actuary magazine, which is the official magazine of the Institute and Faculty of Actuaries. Now, coming back to the mortality modeling problem, mortality modeling is aimed to find a good regression function that expresses the log mortality rates for person aged X at the time t in the population Y as function of t, X, and Y. We also define capital T, capital X, and capital Y as three finite sets that respectively contains all the calendar years, all the ages, and all the populations we consider in our analysis. Accordingly, with the Lee-Carter model, the expected log mortality rates log U subscript X and T and superscript Y is equal to IXY plus the scalar product of BXY KTY. In the Lee-Carter model, we have three different types of parameters, two time-independent parameters, IXY and BXY, and one time-dependent and age-independent parameter, KTY. Lee and Carter provide a simple interpretation for each one of these parameters. For example, the IXY parameter is the average force of mortality at age X in the population Y. The KT is the mortality trend in the calendar years T for the population Y. And the BXY is the rate of change of force of mortality for the X for the age X and in the population Y. The estimation of Lee-Carter model involves in a two-step procedure. First, we have to apply a singular value decomposition to estimate BXY and KTY. And second, we have to use time series methods to project the KTY, the time-dependent parameter, in the future. In the original paper, Lee and Carter suggest to consider only the first component extracted by the singular value decomposition. For this reason, in the Lee-Carter model, BXY and KTY are two scalar values. However, if we wanted to discuss the multi-population extension of the Carter, we have to adopt a more general formulation. In particular, we replace the two terms in the scalar product with two two-dimensional real vectors. And analyzing this formulation, we observe that if we choose Q equal to 1, this formulation becomes the traditional Carter model shown in the previous slide. Instead, if we choose Q equal to 2, this formulation becomes the augmented common factor model proposed by Lee and Lee. In particular, this model provides a couple of population-independent parameter Bx and Kt, and a couple of population-specific parameters Bxy and Kty. Last but not least, if we assume that the Bxy parameter is the same for all the populations, this formulation becomes the common age effect model proposed by Kleinov in 2015. Now, the network architecture we propose try to predict the mortality rates at time t sub 1 plus 1 using information available at the time t sub 1. And our network processes as input a population label y in capital Y, which contains information related to region and gender, and a matrix U tilde 0y that contains the log mortality rates for the last capital T plus 1 calendar years, where capital T is a natural number that defines the look-back period. Mathematically, the matrix U tilde 0y collects the log mortality rates for different ages and different calendar years. In this case, our matrix has capital T plus 1 rows and x sub 1 minus x sub 0 plus 1 columns. This diagram shows a graphical representation of our model. We have 3 different inputs, 2 labels related to region and gender, and the matrix of log mortality rates. In our numerical experiment, we chose the look-back period equal to 9. So our matrix has 10 different rows, 1 for each calendar year considered. And our matrix has 100 columns because we consider for the age the full range is 0-99. Our network processes this input and extract new feature from each one of them, and finally calculate the mortality rates of next year, estimating a generalized linear model on this new set of features. Now, we can explain how our network processes each input. In particular, region and gender labels are processed by embedding layers. Embedding in general is a function that maps a finite set of categories in the new low-dimensional real space. Formally lets capital P be a finite set of labels, P1, P2, P, and capital P. An embedding layer maps capital P in the new Q capital P dimensional real space, where Q capital P is a natural number that defines the dimension of the embedding layer, and Z capital P, function of P, is the representation of P in the new embedding space. We process the region and gender using embedding layers. So we map the sets capital R and capital G in new 2 embedding spaces. And we obtain Z capital R and Z capital G, which contains new sets of features that summarize the information related to region and gender. Differently, mortality rates are processed by a neural network architecture specialized to analyze sequential data. The first type of neural network we consider are the recurrent neural network. This type of networks are called recurrent because they perform the same task for every element of a sequence, with the output being dependent from the previous computation. In particular, let's x sub t a d-dimensional time series. A recurrent neural network layer maps the d plus q dimensional real space in the new q dimensional real space. The output of this vector is of this layer is the vector z sub t, which is function of the current input x sub t, and the output of the recurrent layer in the previous time step z t sub 1 minus 1, and each component of the vector z, for example, the component z sub tj, is the nonlinear function phi of the sum of the bias term plus the linear combination of its input plus the linear combination of all the elements of the vector z sub t, t minus 1. In this case, wj0, wjl, and vjk are the network parameters learned during the training process. Second, we consider the one-dimensional convolutional neural network. Convolutional neural networks are originally, in general, are originally developed for image classification, and only recently they are applied to time series problems. In one-dimensional convolutional neural network layer extract feature from sequences data and map the internal feature of the sequence. In particular, if we consider one-dimensional convolutional layer with Q filters, where each filter is a matrix of sites D times M. This layer produces output the matrix Z function of X, and this matrix contains a new set of features that summarize the input information. For example, a generic element of the matrix Z sub Sj is the nonlinear function phi of the sum of the bias term, of course, plus the convolution of JT filter W and the segment of the input data. Now, coming back to the mortality modeling notation, the starting point is the matrix of log mortality rates UT sub 0y. And we process this matrix with a one-dimensional convolutional layer with 32 filters. The output denoted by Z subscript 1 is a matrix which has the same number of rows and Q columns, one for each filter. We further process the output with the one-dimensional max pooling layer of sites 2. The output denoted by Z subscript 2 is a function that has capital T plus 1 divided by 2 rows and Q columns. And finally, we reshape the matrix Z subscript 2 in a vector Z sub F, which encodes the mortality history contained in the starting matrix UT sub 0y. And finally, concatenating these three new sets of features, Z capital R, Z capital G, and Z sub F, we obtain the global vector Z, which is the representation of input data in the new optimal space. We finally calculate the mortality rates by processing the global vector Z with a fully connected layer. In short, a fully connected layer is a function that maps the d-dimensional input data in the q-dimensional new space, and the output of this layer Z is contains a set of new features calculated as a nonlinear function of the input. And finally, we can define the vector Y, which contains the log mortality rates for all ages, as the output of the fully connected layer that processes the global vector Z. It's important to remark that it is equivalent to estimate a multivariate generalized linear model on the vector Z. Now, rewriting our model for a single age, so for a single component of the vector Y, and decoupling this scalar product, since the global vector Z contains Z capital R, Z capital G, and Z sub F, we can rewrite this model in this way. And we can observe here that our model is a generalization of the Lee-Carter model. Indeed, this scalar product plays the same rule of the scalar product Bxy kty in the Lee-Carter model, because we have a static vector parameter and a time-dependent vector parameter, and at the same time the sum of the other three terms plays the same rule of the xy parameter of the Lee-Carter. In particular, in this case, a further decomposition can be done, because the bias term can be considered as a global IX, a sort of average IX over populations. And these two terms define the region and the gender-specific adjustment of the IX parameter. Now we can start to describe the numerical experiment. The first set of experiments is carried out to simultaneously consider all the population of the human mortality database. In particular, we have 76 different populations, male and female population of 38 countries, and we collect mortality data for each T in capital T. We split our data set in two parts, training set and testing set. The first one is used to calibrate all the models. The second one used to measure the out-of-sample performance of all the models. And In the original paper, we consider different architectures. In this presentation, I will focus on only the three most significant architecture. In particular, the first one uses a one-dimensional convolutional layer, and this is the model I described in the previous slides. And the other two architectures consider the long short-term memory, which is a more sophisticated recurrent neural networks. And the machine learning literature defines the long short-term memory as the state-of-art recurrent neural network for time series problems. And the first variant, we investigate two different variants. The first variant consider only the final activation of the layer as output. The second one consider all the intermediate activation. And we compare the performance of these three networks against some well-known mortality models. In particular, we include in our comparison the Lee-Carter model, the two multi-population extension of Lee-Carter, and the deep learning model proposed by Richman and Butrick, published in Annals of Actual Science. And the first column of this table shows the auto-sample performance in the testing set. Here we can observe that, as expected, the two multi-population extension of the Lee-Carter, the augmented common factor model, the common age effect model, produce quite poor performances when all the population of the human mortality database are simultaneously considered. Differently, we observe that the tree networks architecture we propose strongly overperform the Lee-Carter model. In particular, the convolutional Lee-Carter produced the best performance in the testing set. The second column of this table lists the number of population in which each network beats the Lee-Carter, and here we observe that our convolutional Lee-Carter model beats the Lee-Carter in 75 different populations, and this is a good result. This plot compares the Lee-Carter model, the deep learning model, the convolutional Lee-Carter performance in different age. In particular, we here observe that the blue line representing our model lies below to the others, and this suggests that our model is more accurate because it produces the lowest mean square error. And our model beats the Lee-Carter in all 100 age considers, and beats the deep learning model in 95 different ages. Here, this plot further compares these three models. In particular, here we observe the average residual in different ages and different population. Here we can observe that the Lee-Carter model produced the poorest performance because we have a large red zone, and this means that the Lee-Carter model overestimate the future mortality rates. The performance improves when we consider the deep learning model, and further improves when we consider the convolutional Lee-Carter. Here we observe a large white zone, and this means that our model produces residuals close to zero. In order to further validate our model, we carried out the second set of experiments analyzing the United States mortality database. In this case, we have 102 different populations. We carried out the same analysis, basically. And again, we observed that the tree network strongly overperformed the Lee-Carter. Here, the convolutional Lee-Carter model and the second variant of long short-term memory produced the same out-of-sample performance. We also compared the mean square error in the different populations. Here we observe that the blue points representing the convolutional Lee-Carter model lie below to the red ones. So our model is more accurate in almost all the population. The only population in which the Lee-Carter beats our model is the female North Dakota population. However, the performances are quite similar. Here again, we compare the performance from an age point of view, and again, we observe that the Lee-Carter model produces a higher mean square error, except for the range 22-26, where the Lee-Carter seems to work very well. And finally, we conclude our paper trying to understand what the network learns during the training process. In particular, I provide the simple interpretation for each term of this model, and the bias term can be considered as a population independent X parameter. In order to check what the network have learned during the training process, because this parameter is a weight calibrated during the training, we plotted WX0 for all ages And we observed that these parameters showed the same shape of the classical life table. This suggests that our model learns the differences among the age. And the other interesting point is the embedding region, the regional embedding Z capital R. In particular, this function maps all the region in the new embedding space. In our numerical experiment, we set the dimension of the embedding space equal to 5. So the network maps all the region in a 5-dimensional real space. And in order to explore the representation learned by the network, we reduce the dimension of the embedding space from 5 to 2 using a principal component analysis, and we extract only the first 2 components. And we plot all the region in the new bivariate real space. And we surprisingly observed that the embedding space learned by the network is very similar to the regional maps of the United States. In particular, we carried out a k-means cluster analysis, and we extract 4 different clusters, and each cluster contains a region located in a particular area of the United States. For example, the first cluster contains all the region located in the south of the United States. For example, Arizona, Florida, New Mexico, and Texas. And this is quite interesting because our network is able to reproduce the geographical map of the United States only by processing mortality data. The main conclusion of this work is that deep learning models provide, of course, new opportunity for mortality modeling. In particular, this model can produce more accurate mortality forecasts of the well-known mortality models. However, the most crucial point in the use of this model is to find the best architecture. Indeed, this step can be really challenging sometimes. Thanks for your attention, and thanks for this opportunity.
Salvatore, thank you for your presentation. There was a question in the past, I have to say, I apologize for having overlooked the chat, but I was focusing on your presentation by Alberto Sperti, who was asking about the training and testing set that you had on slide 12. Alberto is asking, didn't you use any validation set?
One moment.
Yeah, you have to go backward. Yes, so slide 12. Alberto is saying that he only sees training and testing set. Didn't you use any validation set?
Yes. One moment. Okay. During the presentation, I skipped the description of some parts of our analysis. In particular, I didn't describe the validation, but we have carried out the validation step during the training. In particular, in this set of experiment, we split, first of all, our data in 2 parts, the training and the testing. The training data contains the log mortality rates for calendar years between 1915 and 1999. And the testing set contains the log mortality rates for calendar years between 2000 and 2016. The first set is used to calibrate our model, and during the training, we carried out the live P-out validation. In particular, this is the same procedure employed in Richman and Wutrich and their paper published on Annals of Actuarial Science. Basically, we further split during the training process the training data in 2 parts: the validation set and the real training set. The validation set contains the last 5% of the training data, and the real training set contains the remaining 95%. And during the training, we calibrate the weight by processing only the real training data. And in each epoch of the training process, we calculate the auto-sample accuracy on the validation set. And we save the weight configuration that produce the best performance on the validation set. We carried out this process for all the network architectures we investigate in this paper. And this is really important because in this way we have a model with a good out of sample accuracy, and we are able to fight the overfitting, because if we don't know, if we don't use the validation set, our model can produce poor out of sample performance. This is the answer.
Yes,
I hope.
Thank you. Then we have another question by Pietro Milosevic. He's asking, when modeling multiple populations, can coherent forecasts be achieved within the deep learning algorithm?
In this paper, we don't work on this point, but we hope to work on this part on a future research, basically, because this paper is under review and we received the same comment from one of the referees, so we are working on this,
including
this is of course interesting, but in this paper for now is focused on the out of sample accuracy of this method, and we try to understand why these deep learning models are more accurate than the multi-population mortality modeling. In the future research, probably we should to address this question, but also, for example, the analysis of the uncertainty of the prediction produced by these models.
Is there any relation with the size of your sample you use to test and the size of the data?
Yes, in this set of experiments, the training set is a sample with 2662 different observation, and the testing set contains 500 units from more or less. You can find the details in the papers. However, the size is something like this. We have 2,500 observation in the training set, and 500 in the testing set, basically.
And if you reduce or you modify the size of your data sets, your deep learning method is always superior.
Before this stage of experiment, we carried out another set of experiment considering only the data in the training set. In particular, we split this set in two parts. The first one consider the calendar years between 1915 and 1990, and the second one contains the time window of 91-99, and we observed the same result. In other words, our model, the convolutionally Carter model, also in that case produced the lowest misperformance, and produce a good performance on the large set of human populations.
Okay, thank you, Salvatore. Any other question? No, apparently there are no other questions in the chat. So let me just wait a couple of seconds to see whether or not anyone have additional questions. Doesn't seem the case. So in that case, thank you again to Salvatore.
Thank you.
I invite Niccolò Urbinati, who is our final speaker for this session.
Okay.
Join us if possible. Niccolò, welcome. We still can't see you. We can hear you perfectly and we can see your screen, but we can't see you.
Okay, so...
Okay, now we also can see you. Welcome again. Okay. Okay, so Niccolò, thank you. Niccolò is gonna present a paper entitled Walrasian objection mechanism and Mas Colell's bargaining set in economies with many commodities. So the floor is yours, and you have around 25 minutes for your presentation. Thank you.
Thank you very much. So if everything is fine with the visualization of the slides, okay, I think we can start. And let me start by welcoming you to this last presentation of the session. As it has been said, I am Niccolò Urbinati. And basically today I'm here to discuss with you about competitive economies with many commodities. So those situations in which the specific economic phenomena we have in mind can only be studied with an infinite dimensional commodity space. In this scenario, we are going to focus on those features of competitive economies that are usually studied thanks to these two notions that give the title to the presentation. So the Walrasian objection mechanism and Mas Colell's notions of bargaining set. Now we'll get to a formal description of these two concepts in a few slides. By now, let me just tell you that both of them have been introduced and studied in the framework of economies with a finite number of commodities, and none of them has been explored in the infinite dimensional settings yet. So what we want to do today basically is trying to fill up this gap, try to understand under what circumstances we can extend the standard analysis of these two concepts from the case of an economy with a finite number of commodities to the case of an economy with an infinite dimensional commodity space. But before we do that, let me convince you why we are interested in this kind of extension. So why it is important to consider economies with an infinite dimensional commodity space. Now, I've mentioned that there are many relevant economic phenomena that can only be studied in this framework. It can only be studied with an infinite dimensional commodity space. Just to make an example, think of situations in which consumers not only care about what they receive from the market, but they also care about when they receive it, where they receive it, what is the state of the world in which they receive a certain good. It is clear that if we want to embrace all these parameters in a single model, we need to work with an infinite dimensional commodity space. To put it in another way, if we limit our attention to economic models with a finite number of commodities, we are limiting our economic analysis to a finite number of places, dates, moments, states of the world, all right? So there are a few other reasons in the literature why we should be interested in this kind of models, but by now it is just important for me to be clear of the reasons why we want to study these kind of extensions, all right? So let us go back to our main problem, which is to study the Walrasian objection mechanism and Mas Colell's bargaining set in economies with an infinite dimensional commodity space. I will focus primarily on the notion of Walrasian objections. I will do that by considering the following three questions. So first of all, we'll try to make sure we all understand what we mean by Walrasian objection. What is the intuition we want to formalize with this notion? Then we can ask ourselves, why do we think that Walrasian objections are relevant in the study of comparative economies? So what kind of information we can obtain on the economy by studying how the Walrasian objection mechanism work? And only after that, we can move to the problem of formalizing all these intuitions in a proper mathematical model. We will do that in three steps. We'll first look at what is usually done in the case of economies with a finite number of commodities. So what are the main results that can be obtained in this framework? And then we will try to understand what are the difficulties that make it hard to extend this kind of a result to the case of economies with an infinite dimensional commodity space. Only after that, we will start to look for conditions under which this result in the intuition we have described can be properly replicated in the environment we are interested in, right? So this is the program for today's presentation. If there are no questions, I think I can start, and I can get started with a very informal description of what we mean by Walrasian objection mechanism. Now, I told you I was going to talk about comparative economies. And one of the reasons why we're interested in comparative economies is that we can study optimal allocation of resources as the outcome of a fully decentralized interaction between agents. In a state of equilibrium, agents not only conform passively to the price system, but there exists no group of agents that can improve upon the equilibrium allocation. So no group of agents is effective, and so there is no incentives from agents to look for coordination among them or to form strategic alliances. So all this is to say that in a competitive equilibrium, agents should act solely in the pursuit of self-interest, in full independence. But what happens when we move outside a state of equilibrium? Even in this case, we might be interested in studying processes that are fully decentralized, that do not require any form of coordination among the agents. In other words, we might expect that whenever F is a non-competitive allocation, it is always the case that a group of agents can improve upon F without recurring to any centralized organization, with a fully decentralized process. And this is the idea that lies at the foundation of the so-called Walrasian objection mechanism. Very informally, it can be described as follows. Now imagine that an allocation is proposed to the agent of an economy, all right? And imagine that the agent of the economy can choose between accepting the bundle that has been proposed to them through the allocation F, or joining a market regulated by a price system P. Now, if F is not competitive, and this is important, there will certainly be a group of agents that will find it convenient to reject F and to trade their own endowments at the given price system. This is to say that the deviating agents will be able to find in their demand set a bundle that they prefer to what has been promised to them through the allocation F. Now, if all these bundles are compatible with each other, which is to say that the demand of the deviating coalition is supported by their supplies, then these agents can actually implement this plan and form what we call an objecting coalition. This kind of objection is what we call a Walrasian objection. Now we see why Walrasian objections are important. On the one hand, this is a fully decentralized process. It does not require any form of coordination among the agents, but at the same time, it has some serious problems. For example, given out an allocation F and a price system P, it will be very hard that this process leads to the formation of a Walrasian objection. So a question we may ask is, when is this process effective? When is it the case that whenever we consider a non-competitive allocation, we can always find a price system P such that this process leads to the formation of a Walrasian objection? So this is the question we will keep in mind for the rest of this presentation. And this is the question that Mas Colell had in mind in his famous paper of 1989, which is the one in which he introduces the notion of bargaining set and introduces the notion of Walrasian objection. So as we can imagine, the main result of bargaining set of Mas Colell deals with this question. In fact, Mas Colell proved that in a competitive economy with a finite number of commodities, it is the case that every non-competitive allocation can be blocked with the process we have defined before. So this is the problem we will keep in mind, and this is what we will try to extend to our infinite dimensional settings. Okay, but why is it important? Why do we think that this is a relevant question and we want to work on it? Well, we have already seen that the process that describes the Walrasian objection is fully decentralized. It does not need any form of coordination among agents. This is important, especially as we consider large economies in which the lack of communication or a centralized institution may make it extremely hard for agents to come together to form coalitions and to coordinate their actions. Another important property is that Walrasian objections in most of situations are justified in the sense that they cannot be in turn counter-objected. This is significant because it introduces some form of stability in the objection mechanism and because it prevents the reaction of other agents. A last property that I would like to focus on is related to the fact that the Walrasian objection mechanism is price-based, and as such, it treats the same way agents with the same characteristic. We usually define this property as anonymity because the process does not look at the name of the agents, but only their attributes. This is an important property because it simplifies the description of an objection, and at the same time, it implements some form of equity or fairness because there is no discrimination among agents with the same characteristics. So we have seen the intuition behind the definition of Walrasian objection. We have seen the question that we want to formalize, and we have understood why we think this question is significant. Let's move to the proper formalization of this problem. And as I told you, we're going to try to do this in the settings of an economy with many commodities. Now, the model we will consider is very standard. We have a commodity space that is an order separable Banach space whose positive com has an interior point. Prices are defined as the vectors in the unit simplex of the topological dual of the commodity space, while agents will be represented as the point of a measure space. Here, as usual, the elements of the sigma algebra represent all the coalitions that can be formed in the economy. Every agent will be characterized by a consumption set that is prescribed through the consumption set correspondences, and allocations are defined as all the integrable selection of such a correspondence. Among all the allocations, we will give a special importance to the initial endowment, which is the description of how the resources are initially distributed among the agents. And every agent will be characterized by his preference relation, so which is a binary relation on his consumption set. We'll make some further assumption, but again, all these assumptions are very standard in models of economy with an infinite dimensional commodity space and a measure space of agent. We assume that the consumption set correspondence is measurable, is weakly compact and convex valued. We assume that there is some form of strong survival assumption on the initial endowment, and then we assume that preferences are weakly continuous, locally associated, and also measurable. Okay, so in this framework, we can formalize many notions we are familiar with in a standard way. For example, we can say that the budget set of the agent P is formed by all the bundles that the agents can afford at a given price system, while the demand set of agent T at the price system P are formed by all the bundles in his budget set that maximize his level of satisfaction, that are maximal with respect to the preference relation. An allocation will be said to be competitive if it is feasible and if there exists a price system P such that the allocation assigns to every agent in the economy a bundle in his demand set. All right, so very standard definition. Even the definition of objection is quite standard, very similar to that we can find when we study the core of an economy. So we will say that the coalition can object a given allocation if there exists another allocation that is attainable by the coalition S, that is weakly preferred to F by almost every agent in the objecting coalition, and that is strictly preferred to F by at least a positive share of the agents, right? With this definition, we can finally introduce the main character of this presentation, which is the notion of Walrasian objection. So an objection SG is Walrasian at a price system P if, whenever we take an agent inside the objecting coalition and X is a bundle that he prefers to G, then X is a bundle that the agent cannot afford. At the same time, if T is not an agent in the objecting coalition and X is a bundle he prefers to F, then X is a bundle that the agent cannot afford. It's a very syntactic definition, so let me spend a few words on it. So let me bring the definition to the top of the slide and make the following observation. If SG is a Walrasian objection to F at the price system P, then whenever T is an objecting agent, so belongs to the objecting coalition, it means that the agent was able to find in his demand set a bundle that he preferred to what had been promised to him through allocation F. At the same time, if T does not belong to the objecting coalition, it means that whatever he could get from the market, he preferred F over that bundle. So you see, these are exactly the 2 points we mentioned when we described intuitively how the Walrasian objection mechanism works. So all this is to say that this definition of Walrasian objection seems to formalize quite correctly the intuition we have described informally. Now that we know what we mean by Walrasian objection, let us state our main result. I told you that it was proved by Mas Colell in the finite dimensional settings. So what Mas Colell did, he considered an economy with a finite number of commodity and non-atomic measure space of agent, and he was able to prove that whenever F is a feasible and non-competitive allocation, we can find a Walrasian objection against it. I don't want to go through the proof of Mas Colell. However, let me point out that there are 3 important ingredients that he bases his proof on: the compactness of the set of prices, the upper hemi-continuity of the mean demand correspondence, and the strong version of Lyapunov's theorem on the range of vector measure. This is important because Lyapunov's theorem is known to fail whenever we consider an infinite dimensional commodity space. So the question becomes the following: how can we extend the theorem we have just seen to the infinite dimensional settings? Unfortunately, things are not that easy for a few reasons. First of all, in the infinite dimensional setting, the set of prices is not norm compact. The mean demand correspondence is not upper hemi-continuous, at least with respect to the weak star topology on the set of prices. And the theorem of Lyapunov does not hold, as I mentioned before. So the idea we decided to follow in this work was to consider delta, the set of prices endowed with the weak star topology, so that, thanks to the Banach-Caloglu theorem, we can ensure that this is a compact set. Move the attention from the demand correspondence to the extended demand correspondence, following an expedient that was introduced by Potzek. And then, since the non-atomicity of the measure space was no longer enough to ensure the validity of Lyapunov's theorem, we look for ways to enrich the structure of the measure space of agents in order to obtain new versions of Lyapunov's theorem that can be extended to the infinite dimensional settings. All right. So how do we do that? Let me introduce you to the notion of saturation. Now this may look a little complicated, so let me guide you through the slide. It is the following: a measure space is essentially control generated if the set of all measurable set can be approximated with a countable family. So this is a kind of measure theoretical equivalent of the notion of separability. A measure space is said to be saturated if, whenever we take a non-null element of the algebra, the principal idea generated by that element is not essentially countably generated. So saturated measure spaces are spaces in which the structure of all the measurable sets are actually extremely complex, rich. They're very well known actually in the literature, but you might have heard of them with different names. Now the question becomes, why do we think that saturation is a good property we should consider in our framework? Well, in a way, we could say that saturated measure space represent the natural extension of the idea of non-atomic measure space. Why is that? First of all, every saturated measure space is non-atomic, and this is the least we could ask. Secondly, it is possible to prove some infinite dimensional extensions of Lyapunov's theorem that hold even in the case of infinite dimensional commodity space. So in a way, just like non-atomic measure space are the natural representation of agents in a competitive economies with a finite number of commodities, we could argue that saturated measure space are the natural representation of agents in a competitive economies with an infinite dimensional commodity space. So let's see if this property of saturation is enough to obtain our result. So we said we wanted to extend the Mas Colell's result, and we wanted to change the assumption on the finite dimension of the commodity space. Together with that, we want to change the assumption on the non-atomicity of the measure space of agent. Remember, I said we wanted to enrich this measure space. That's exactly what we did. In fact, we were able to prove this theorem, according to which if the commodity space is infinite dimensional and the measure space of agent is a saturated measure space, then every feasible and non-competitive allocation can be objected with a Walrasian objection. So this is the main result, what we could obtain, what we could extend from the case of economies with a finite number of commodities. Now let me make just a few observations on the bargaining set. In order to define the bargaining set, we have to make sure we all have the same idea of what we mean by counter-objection. So given an objection as G, a coalition Q can counter-object S if there exists an allocation H that can be attained by the coalition Q that is strictly preferred to G by the agents that belongs to both of the coalitions and is strictly preferred to F by the agents that belong to Q but do not belong to S. So in a way, a counter-objection represents a way in which agents improve not only on F but also on the objection that has been raised. These are all standard definitions. We say that an allocation is a core allocation if it cannot be objected. We say that an objection is justified if it cannot be counter-objected. And we say that an allocation belongs to the bargaining set if it is feasible and there exists no objection against it that cannot be counter-objected, that are justified. So the main result for the bargaining set is related to this one. Every Walrasian objection is justified. This was proved by Mas Colell in the finite dimensional case. We've extended it to the infinite dimensional one. Another result that was proved by Mas Colell for non-atomic measure spaces is this corollary. If the measure space of agent is saturated, then competitive allocations, core allocations, and allocations in the bargaining set, they all form the same set. So these three solution concepts coincide. The proof is actually quite simple, but I think I can just quickly lead you through this. So one of the inclusion is obvious because we already know that competitive allocations cannot be objected. And we know that if an allocation cannot be objected at all, then of course it cannot be objected with a justified objection. To prove the other inclusion, we use the result we have proved before. We take an allocation that is feasible, but is non-competitive. And we observe that thanks to the result we have proved, we know that there exists a Walrasian objection against it. Now, the theorem in this slide shows us that every Walrasian objection is justified. And so F cannot belong to the bargaining set because we have found an objection to F that is justified. All right, so let me quickly guide you through the conclusions. So this is more or less what we've done. We have formulated the notion of Walrasian objection. We have discussed about the reasons why we might be interested in this kind of concept. We have proved that for a saturated economy with an infinite dimensional commodity space, it is always possible to find a Walrasian objection against any non-competitive allocation. So the Walrasian objection mechanism is effective. And we've proved the equivalence between competitive allocation, core, and bargaining set, always in the case of saturated economies. Other things we have done in the paper, but we have not discussed here, we gave new characterization of Walrasian objections that hold even when the space is not saturated. And then we gave alternative proof of the core-Walras equivalence and of the existence of equilibria in saturated economies with an infinite dimensional commodity space. For the next steps that we want to undertake, we could, for example, try to weaken the assumptions on the commodity space. We could try to understand if we can obtain similar result by assuming that the positive corner of the commodity space has empty interior. In this case, we expect to use some properness assumption, or we can drop the assumption that the Banach space, that the commodity space is a Banach space. For example, we can follow Potsex. We can then include production in our model. These are two examples, one for the existence of equilibrium, and that's for Mas Colell bargaining set, but always in the case of finite dimensional economies. Or we could weaken the assumptions on preferences. We could, for example, study the bargaining set with incomplete preferences or in the presence of externalities. These are all ideas that we might be working on, but we have not obtained any result in this direction yet. So I think this would be it.
Thank you. Thank you, Niccolò, for your very effective presentation. So let me ask whether or not there are questions in the chat. Apparently the chat is still empty. No objection, because your talk was very fluent and very precise. So I think everyone now has got a perfect idea what you do and also what you aim to do in your very ambitious research agenda. Congratulations, it's very interesting.
Thank you.
So I don't see any, so let me leave. No, there are no questions. No. Okay, so in that case, let me thank you again, Niccolò, for your great presentation. And let me thank all our 4 young speakers for the great presentation. It has been a pleasure to attend this session. And in particular, let also me congratulate you on your work and your results. Good job, well done. I think that now we have a time time for a break. It's time to have a break and have lunch. And I think that we meet again at 2 p.m. for the next AMASES session. Thanks again to everyone, and also thanks to all attendees. Thank you.